So we're going to start off something that should be familiar to us, applying some formulas that deal with the things you're doing this semester. And one of them we're going to be talking about material weight and density. And density can be listed in a lot of ways. The traditional scientific way of listing density is a weight per unit of volume, or weight divided by volume. So the relationship is obvious. There you would find the weight from the density if you knew the volume or the size of the object. The weight would just be the volume times the density. Well, in practice, finding the volume is often kind of clumsy to do. So there are more efficient ways of doing this. So alternative ways of listing density outside of the traditional scientific way is to do a weight per unit of length. So this is usually typically in pounds per foot. So if we have a steel bar, or I should say any sort of metal bar, the weight of that metal bar is equal to the length of the bar times the density. Now, the units that your textbook uses for density, rather than listing as density, they call it a weight per foot, which is a density, weight per length. So there are tables in your book that list this stuff. In your big book, the Industrial Mechanics, it's page 137, or 147, yeah. Where you see that top table, weight of steel and brass bar stock. So for example, let's say we have a 1 inch or 1/2 inch thick round steel rod at 20 feet long. So first we have to look up in the table. There's two things we need, 1/2 inch and round. So we got round steel, go down to 1/2 inch on the side. You guys see the density given there? What is it? .667, yeah. I'll wait and make sure, does everybody find that? Perfect. Yeah, that is page 147 if you're looking for it. So then that means to find the weight of that steel bar, we take the length here of the 20 feet times that .667. The units on that are pounds per foot. Now, normally I would leave the units off to simplify the calculation, but I put them on here in the first one because we can see how the units work together. This is just feet. If you wanted to make it a fraction or a rate, you put it feet out of 1. You can see in the units, the feet will cancel out. There's feet on top of one unit on bottom of the other, leaving us with just pounds. So 20 times the .667, 13.33, yeah. Yeah, 34 pounds. So a relatively simple calculation, just finding the correct numbers. So I'm going to have you guys try one here. 1.5 inch square steel at 10 feet long. So find the weight of that quick. See what you come up with. Perfect. So you got 7.7 pounds per foot is the density of it. So we have our 10 feet of length times the 7.7 pounds per foot is 77 pounds total. Now the next adaptation to density that we use in practice is per square foot. So we might list it as weight per a unit of area, square foot or square inch. Typically we're doing square foot here. But it has to be specified that that area is for a given thickness. So really we're looking at volume. We're just taking an area and specifying a thickness. We're using the volume, or using the area and the thickness to create a volume, but we're calling it area. So this would be the next table down on that page 147, where we're seeing the weight for a steel plate for a given thickness. This is per square foot of the area of that plate. So here the weight is just simply given as the area times the weight per square foot. And then your textbook here, the industrial mechanics, uses times Q, where Q is just a number of sheets. Other textbooks I've seen just do the area times the weight per square foot. You get the weight of each sheet, and then you could multiply by the number of sheets later. So it really doesn't matter. So the example we're going to use here, let's find the weight of 6 plates of 4 foot by 8 foot steel at 1/4 inch thick. So from that table, what is the weight per square foot for 1/4 inch thick steel? 10.2, perfect. And technically the units there is pound per square foot. So the weight of this, we have an area. How do we find the area? Oops, back up here. Yeah. Length times width. So the area is the 4 feet times the 8 feet. So 32 square feet. So I have an area of 32 square feet times that 10.2 pounds per square foot times, there are 6 plates. So 6 would be our Q. And so again, we can see the square feet cancel out. Square feet on bottom for the pounds per square foot, square feet on top for the 32 square feet. And so the only unit we have left is pounds. The 6 had no units on it because it was just a number of sheets, just counting. And so we multiply that out. My calculator will come up here. There we go. That sounds good. Yeah, 1958.4. Perfect. Any questions on that? So this allows us then to build up to finding the weight of a vessel. So by vessel, we're just meaning a container. And what we're only going to look at here is a cylindrical container. Cylindrical vessel is the term that your book uses. And we're going to find the weight using this last piece that we looked at as the weight per square foot. So we're going to find the surface area of this container, the thickness of its walls, and then use that to find a weight from it. So we need to first be able to find the surface area of a cylinder. Now I am going to qualify that as a cylinder with an open top. Because technically we're finding the surface area of a cylinder. There's a bottom and a top to it, but we're looking at a container. The top is open to fill it. So here's our cylinder. We have really two pieces that we're looking at finding the area of. We have the bottom. So to find the area of the bottom, what shape is the bottom? It's a circle. And so to find the area of a circle, what's our formula? Does anybody remember? Pi times radius squared. Perfect. So let's put a number on here. Let's say that this is, let's put it 3 feet across, 3 feet in diameter. So now that 3 feet of diameter gives us a radius of what? Where'd the 1.5 come from? There you go. Radius is only halfway across. So it was the 3 feet of diameter divided by 2 to give us a radius of 1.5. So our area here is going to be pi. We're just going to use 3.14 for pi times 1.5 squared. For those of you that are new, if you don't know how to enter squares or powers in your calculator, most of you have either, depending on your calculator, it's called a caret key that looks like that, or you might have an x to the y or y to the x key. Most of your cell phones have that x to the y or y to the x key. So I'm just going to type in 3.14 times 1.5. Now I actually have an x squared key. Some of your calculators have a designated x squared key instead of using the power key. So it's 7.065. That is square feet for the bottom. Any questions on finding the area of the bottom? So our next step then is we have to find the area of the sides. Well, if we think of this as being our cylinder here, we just found the area of the circle on bottom. Well, the sides, if we cut it down the side, we can unroll it and it becomes simply a rectangle. The height of that rectangle is just the height of our cylinder. Let's say that we have a height here of 5 feet. So this is 5 feet. How do I find this length of this rectangle? Well, where does it come from? We think of the bottom of our cylinder, it is circumference of a circle. So the formula for the circumference of a circle is just pi times diameter, right? So that pi times diameter is the length of the rectangle. The width is just going to be the height. So the area of the sides is pi times the diameter times the height. So for this vessel here, we're going to go 3.14 times, what goes in for D? 3 feet. And for H? 5. So give us 47.1 square feet. Any questions on finding the area of the sides? So then the area of the whole vessel, I'm just going to add the area of the bottom plus the area of the sides. So 7.065 plus 47.1, 54.165 square feet. So why did we find the area, all this surface area? Well, because then to find the weight of the vessel, it is simply the area of the vessel, that's the number we found here, times the weight per square foot for the appropriate thickness. So for this container, let's say we tell you that it is, what number? Let's put in 1/8 inch thick walls. So that means page 147, that lower table, the weight per square foot, we're going to look up 1/8 inch, and we get a weight per square foot of 5.1 pounds per square foot. So the weight of this vessel would be the area of our vessel, 54.165 square feet, times the weight per square foot, 5.1 pounds per square foot. Again, the square feet just cancel out. 54.165 times 5.1, 276.24. We'd usually round to 1 or 2 decimal places. So about 276.25 pounds is the weight of that container. So I'm going to have you in your notes try for me, find the weight of a 4-foot diameter, 6-foot tall vessel with 1/4 inch thick walls. We'll give you a couple minutes and we'll go over that. So you might not be completely done, but let's take a look and see if you're heading in the right direction here. So first we're going to find the area of the bottom. How do we find the area of the, what numbers do I put in here for the area of the bottom? 3.14, yep, times radius squared. So our radius is going to be 2. Half of the 4. 4 foot's the diameter, so 2 foot radius. So what is that? 12.56 square feet. For the area of the sides, 3.14 times what? Perfect. Times the diameter of 4, and then the height of 6. So what is that? 25.12? Nope. Yeah, you're right. I'm wrong. What'd you get? 75.36. That sounds better. So 75.36 square feet. And then, of course, the area of the whole vessel is just found by adding those two up. So what do we get? 87.992, thank you, square feet. So that's the area of the whole vessel. From there, we find the weight by taking that area times what? Perfect. The 1/4 thickness, we look in the table and we get the 10.2. Perfect. Multiply that by 10.2, what does it give us? 896.78 pounds. Perfect. Any questions on that? There's a lot of steps there, so that one's easy to get a little lost in. So let's talk about a rope or a cable bending around a pulley. This textbook tends to refer, they don't use the term cable, they just tend to use the term steel rope. Same thing, it's basically just a cable. And so when we're looking at any rope or cable bending around a pulley, the first thing we have to worry about is something called a bending ratio. And where that comes from is, of course, a pulley is a circle pretty much. And our rope or cable is going to lay over that pulley. It may not be a complete half of turn, but it's going to have some sort of bend like that. And when that rope bends over the pulley, because it's not straight anymore, the fibers on the inside are compressed. They're being pushed together. And the fibers on the outside are being stretched. They're being pulled apart because that rope isn't straight anymore. Think about it. If you bend a piece of plastic, often the side on the outside of the bend cracks because that surface is being stretched. And if it can't stretch that far, it breaks. So when a rope or a cable bends around a pulley, it potentially reduces the strength of that rope. So we make allowances to the strength of that rope based on the amount of bend, and it's the bend ratio that determines that. So the bending ratio, the ratio of the bend, is the diameter of the pulley. Big D is the diameter of the pulley, over little d, which is the diameter of, we're just going to use rope rather than saying rope or cable all the time. So let's say I have a 6-inch diameter pulley. And we'll go with a 3/8 inch diameter rope. Our bending ratio, what's going to go on top? 6 inch, and on bottom, 3/8. If we do 6 divided by 3/8, now if you're going to do this on your calculator, if you have a fraction calculator, you can enter the fractions. But if you don't have a fraction calculator and you're just entering this on a cell phone calculator or whatever, what you do is 6 divided by, then you put parentheses around 3 divided by 8, and then close the parentheses. That'll give you the correct calculation, which is a 16. So we have a bending ratio of a 16. Well, what does that 16 tell us? Well, we have to flip ahead in the book to page 156. On page 156, we have a table for bending ratios. I think I've got this one on my desktop, so let me pull up a copy so you can see a big version up here. So it's called the bending efficiency chart, and it basically is saying from this bending ratio, raise this size a little bit. We can find an efficiency. So our bending ratio here was a 16. So trace that up. Now this is not going to be exact. We have to estimate. So this is showing just under 90%. 85 would be right there. So I'm saying this is probably somewhere around like an 88 or 89%. We're going to have safety margins in this anyway. That's one of the things we'll talk about. Any sort of overhead lifting, you have huge safety margins. I mean, like you reduce the expected strength of it by dividing by 4 or 5 at least. So if we round it up to 90%, it would probably be okay. I'm going to call this for now 89%. When we do the worksheet or quiz on this, just write down the percent that you read off the chart, and I'll make sure that when I grade it, I account for if you read it a little differently. Because to be honest, you cannot look at this exactly and tell, is that 88%, 89%, 88.4%? I mean, it's not exact. In practice, they do have tables or actually little app calculators where you plug in the bending ratio and it'll spit out an exact efficiency for you. So that 89% efficiency tells us that whatever the rated strength of that rope is, we're going to multiply the rated strength by 0.89 to get the applied strength, what we're able to use for here. So let's put that in practice. So we're going to determine the rated load for a rope. So the rated load after bending is just the rated load, the full rated load, times that bending allowance, that bending efficiency off the chart. Now, the symbol that is used in a lot of formulas for bending efficiency, up here we said, this is the bending ratio. This 89% or 0.89 is the bending efficiency. It looks almost like a script Z. It's actually the Greek letter eta. And that is the bending efficiency, or that percent from the chart. So our rated load after bending is this full rated load times that bending efficiency. So let's say that up above we had a rope that is rated for, what did we say that was? A 3/8 inch rope. Let's say it is rated at 1,400 pounds. So its rating after bending will be that 1,400 pounds times the 0.89. So 1,246 pounds. So you can see that's a significant reduction in the rated load for that rope. So let's put this all together. We're going to determine a rope's rated load after bending for a 1/2 inch diameter rope rated at 1,500 pounds on a 5-inch pulley. So what is the first step we need to do? There we go. We need the bending ratio, the ratio of the bend, which is the diameter of the pulley over the diameter of the rope. So yes, 5 inches over 1/2 inch gives us 10. So that is the bending ratio. What do we do with that? We look at our efficiency chart. Yeah, as I said, right around that 85, 86. I would probably, just to be safe, I'm just going to call it 86% or 85%. That way we know that we can definitely lift at least that much or more. So what do we do with that 85%? Yeah, we find the rated load after bending is the rate, the 1,500, the full rated load, times that 85%, or 0.85. $1,275, perfect. So our now rated load after bending of 1,275 pounds for that rope. Any questions there? So then the next step from all of this is something called a working load limit. Now what we actually found up here is really a working load limit. But how do we get to that? We said that this rope was rated at 1,500 pounds. Well, that 1,500 pound rating was a working load limit. That rope should be able to hold a lot more than 1,500 pounds, probably closer to 6,000 or 7,000 pounds. So how did we end up with a working load rating of only 1,500 pounds out of it? Well, this is where I had mentioned earlier that idea of a safety factor. So a safety factor takes into account variation in conditions, variation in the rope itself or the cable itself or whatever piece of material working with, variations in climate, temperature, humidity, stuff like that may affect things. Now, this next part you don't have to write down. This is just going to kind of a little bit of background information. You guys have heard of the bell curve, right? Okay. So the center of the bell curve is average. On average, a rope that's a 1/2 inch in diameter has the rating, the strength rating, that we're going to be pulling off a chart in just a little bit. Actually, that chart's also on page 157. It shows for like a 1/2 inch rope, fiber core showing 20,800 pounds of rated strength. But that's average. That would be right in the middle of this curve. Some ropes can hold more than that. Some going to hold less than that. Well, how much less? Well, there's something called a standard deviation in statistics that tells us how wide this curve is. This bell curve is a statistical function. It's called the normal distribution or normal curve. Well, we're not going to get into calculating the average or the mean and the standard deviation and all that, but just know that as you go out, whatever that standard deviation is, and again, you don't need to know this percent, but 68% of all ropes will be in that range. It's one standard deviation less than average or one standard deviation more than average. Now, that standard deviation for a 20,000 pound average, that could be 300 or 400 pounds. So there might be 68% of your ropes are going to be between 20,000 and 21,000 if you have that 20,500 rating. But it's still possible to go outside that range. 95% will go out within 2 standard deviations. So there's a portion that would be further out. Again, if that's a 400 or 500 pound standard deviation, it could be 1,000 pounds less or 1,000 pounds more. And you can keep going. At 3 standard deviations, it's 99.7%, which means pretty much all of the ropes that we use are within 3 standard deviations of that average. But again, we're not going to go through the trouble of calculating that standard deviation. But part of what the safety factor is doing is accounting for that variation in the ropes. So even though it says it's rated at 20,800 pounds, there might be some ropes that are perfectly undamaged that might only be able to support 18,000 pounds, and others that might be able to support 24,000 pounds just fine. So we're accounting for that variation in the ropes with our safety factor. The other thing is environmental conditions. Steel cables are very temperature sensitive. If you get into an elevated temperature, they get weak. Humidity affects fibers of a regular rope, of a fibrous rope. The fibers don't stick together as well. They can slide apart in high humidity. So those climate conditions can have a lot of effects. So it seems excessive, but most of our safety factors, so now we're getting back to the part that's actually part of your course. Most of our safety factors are anywhere usually between 4 and 6. So what that means is, let's say a safety factor of 4 for that 1/2 inch rope, say 1/2 inch fiber core rope, that had a rating of 20,800 pounds, our working load limit, our usable limit, gotta make sure is going to be that rating and this is a breaking strength. That is, at that force, we would expect this rope to start to break down and start to break. So it is the breaking strength. Sometimes it's labeled as S with a little break by it. I'll write it. I think that's what your book uses. The strength at the breaking point divided by that safety factor. So we're going to take that 20,800 pounds of breaking strength divided by 4, which means that rope in a working situation, we're not going to use it for anything that requires more than 5,200 pounds of stress on it. Now, you might think about this, look at this and say, well, that's an excessive allowance. But again, there's variations in the rope. Also, the fact that those ropes are not new. You don't just use them once and throw them away. There could be nicks in the rope and stuff like that. I'm sure you're all old enough to remember, was it the I-35 bridge that collapsed in Minnesota? There was a case where they started shaving their safety factors. Most bridges are built with like a 12 to 15 safety factor. So they figure that bridge should hold at least 12 times whatever they expect to be the total weight of vehicles on that bridge. Well, they were doing construction on the bridge, and when they do construction, they do tend to push the safety limits, but they parked all their building materials and all their equipment in one spot. And what that did was it put them to where their safety factor was pretty much 1. It was in the center of the bridge, which is the absolute worst spot.
I drove across that.
Did you? Really? So you missed it by hours.
I took it home because I was like, this is a effing nightmare.
Sure. So that's got to give you a little bit of a jitters thinking about that, huh? Yeah. I mean, so it's just like when you're doing roofing on a house. Most people stack the shingles at the peak. Well, that's at the midspan of the roof truss. That's the absolute worst spot to put them. That gives you the absolute most stress on the roof. The safety margins in the roof account for it, and you don't have issues usually. Well, the same thing here. The safety margins usually account for that construction load, but they pushed it a little too close for one. Had that been a healthy bridge, it would have held. But the other reason for the safety factor is because over time the bridge weakens. Bolts might get loose, pieces rust and get thinner. None of the metal under that bridge is the same thickness it was when it was new. It's corroded. Stress over time causes stress fractures or cracks in that metal. So all those things are accounted for in the safety factors. So what happened there was they used their safety factors twice, their safety margins. They were when they inspected the bridge for wear and tear, they said, yes, it's weakened, but the safety margins will make it safe for use. And then they went on top and threw the construction load in there and said, oh, the safety margins will allow us to put our construction load on here. The overlap caused it to fail. So yes, a safety margin of 4 or 5 times seems extreme, but there's one where a 12 or 15 safety margin did not cover all those extreme circumstances that came together. In engineering, we tend to talk about 10-year conditions and 20-year conditions and 50-year conditions. If you ever listen to the weather real closely, you might hear those. This is a 20-year storm. What that's saying is over a 20-year period, we would only expect to have one storm of this magnitude. So in engineering, when we say a 20-year condition, we would say that over a 20-year period, we would only ever expect to exceed this condition once. Well, yeah, what happened on the I-35 was a 50-year condition. They would expect those conditions to build up maybe once in 50 years, and it hit. So that's why bridges are rebuilt way more often than that. So anyway, let's do an example of this, and then we'll let you guys take a break here. So we're going to do find the working load limit. For, let's do 1/4-inch fiber core with a safety factor of 5. So I'll give you a minute to look all that up, and then we'll go over it. So what is the breaking strength for 1/4 inch? What is it? Oh, you're looking at the final answer.
534.
Yep. 5340. Perfect. Pounds. So that is the breaking strength. So yes, the working load limit would be that divided by 5 for a safety factor, which is what, 1,000 and what?
68.
1,068, like that? Pounds. So you can see that reduces that pretty quickly. Okay, let's go ahead and take a break. We'll start up again at 10:30. So we've spent some time here talking about ropes and cables and bending allowances and stuff like that. Well, in close relation to those are chains. Now, I don't have to define for you what a chain is, but the limiting factor in the life of a chain is something called elongation. Elongation in a chain happens in two forms. Pretend my artwork doesn't totally suck. I am a horrible artist. So anyway, so you have these two lengths linked together here. One form of elongation is the length itself actually stretching out and becoming longer, and that'll cause the metal walls to become thinner as it stretches. I don't know if you've ever stretched metal, but the walls become thinner. In downstairs in room 134, one of the rooms you sometimes use, I have an old tensile tester. I used to do a material engineering course for machine tool, and where we would stretch specimens until they broke. And you could see for stainless steel especially, an 1/8 inch diameter round piece of stainless steel that starts out at 3 inches long, we could actually stretch it over 1/4 of an inch before it broke. But it went from an eighth of an inch thick down to just over a 1/16 of an inch thick before it snapped, because as it stretched, it has to get thinner. It's called necking. Necking or stretching, we can't account for a whole lot in our formulas. But what we can account for is wear. Come on. And what that means is in the joints here, where the two links rub together, the metal wears away. Every time two pieces of metal come together, flex particles of the metal peel off and are lost. Well, as that chain sits there, a chain that just holds steady doesn't wear very fast, but the more it moves, the more those joints move past each other and cause wear, and material will erode from there. Well, as that material erodes, this link is going to move over because it's fitting in further down the line. So as those material wears, the chain itself will get longer, and that's the elongation. So what we want to look at is a percent of elongation. So percent elongation is the change in length over the original length times 100%. Sometimes written, the change in length is the new length minus the used length or worn length over the new length, then of course times the 100%. So for example, let's say we have a chain that is new, is 78 inches long. After 6 months of use, it is now 78.75 inches, 78.75 of an inch long. So our elongation would be I wrote this backwards. This should have been used length and new length. Oops. Sorry about that. Used length is always longer than the new length. Used minus new. So our elongation is the used length, 78.75, minus the new length of 78. Then we'll divide that by the original length of 78 times 100%. So yeah, somebody said it there, the 78.75 minus 78 is 0.75 over 78 and then times the 100%. Now, the percent is just a symbol here. When we do the calculation, we're actually going to just do 0.75 divided by 78 and then times 100. Gives us 0.96. Now we put the percent on that. So this is slightly less than 1% elongation. In practice, and Bob will talk about this more with you as he sees fit, my experience is in practice, you're only allowed up to 1.5% elongation before you would take a chain out of service. Now that 1.5% varies in the usage. If you're lifting from a pit up to ground level, sometimes they allow more. If you're lifting overhead, 1.5% is pretty standard. If you're lifting and you're going to be lifting overhead and transporting horizontally over the top of where people might be, the percent gets smaller. So it depends on the situation, but 1.5% elongation I found is a pretty standard number. So this chain would still be usable. I'm going to have you guys just quickly find the percent elongation for a 122.4 inch chain that was 10 feet new. Now I threw a little bit of a curveball in there. 10 feet new would be how many inches? Okay, good. I'll let you guys go from there. What did we get for elongation? 2%. Good. We subtract there, we get 2.4 inches. Divide by 120 and then times 100 gives us 2. So it's 2% elongation. That chain is probably worn out. In practice, rather than doing this calculation all the time, we a lot of times want to look at finding the maximum working length or worn length of a chain. To do that, we use the fact that when the chain is new, it's at 100% of its length, plus whatever the allowable elongation percent is. So let's say that allowable elongation is 1.5%. So we add 100% plus 1.5, of course, 101.5%. In practice, we're going to convert that. Yes, you're exactly right. We're going to convert that to a rate, or a decimal form of a percent. So 101.5% as a decimal becomes 1.015. All we're doing is dividing by 100. So then our allowable length, let's say that the new length is, let's say we have a 15-foot chain, 180 inches. So then the allowable length (180 inches) times 1.015, giving us 182.7. Now we're keeping this pretty basic here. In practice, you would never measure 180 inches worth of chain and find its elongation, because you have this chain here and it doesn't function the same way at every location on the chain. For example, if it's going over a pulley, similar, one of the advantages of a chain is when it goes around a pulley, unlike a rope, the chain flexes. It doesn't have to stretch fibers on one side and compress on the other. So we don't have that loss of strength. But the problem is the part that is bending around that pulley, now as the chain moves, those links are sliding past each other. So the portion of the chain that would be bending around the pulley is going to wear out way faster than the parts that are staying straight that don't ever have to go around the pulley. So you'd want to be taking that chain and you want to measure section by section from and usually you don't do a single link, but you usually do 3 or 4 links at a time. Say new the length from here to here. If you fold the chain and stretch it out as far as it'll go with those 5 links, find what the new length was, and then now after it is worn, what that length is. And so you'd go section by section on the parts of the chain that you know are going to wear faster. The parts that are bending like that, or any part that, if you have a rigging where you have to push it off to the side and lower it, the part that's going to flex when you have to move off to the side, that part you're going to measure on a smaller scale to make sure that you don't have excessive wearing there. Because you could have a chain, I've seen chains where the total elongation of a 15-foot chain is within specs, but there's individual links that are nearly worn through because they're the ones that were getting all the friction. Okay, so our next concept, we're going to shift gears here a little bit and look at geometry, because we're going to be looking at overhead lifting and slings here in a little bit. Actually, probably won't get to that till next session. But we need to look at the geometry of triangles. Triangles are very important in any sort of engineering application because triangles are a rigid structure. If you think about it, if you have 3 pieces of material, all you have to do is drill through and put pins through the ends to hold them together, and that triangle is not going to flex. It can't move. Whereas if you had 4 pieces of material, if you just put pins through the corners to hold them together, if you push on it, that thing's going to push flat. It's a process we call racking, where it just bends over on itself. Racking means it goes out of a rectangular form into a parallelogram form. So the triangle is what we call a rigid figure. So any type of structural design, we're trying to create triangles. Even in a sling, So if I have something being supported from above by ropes or chains, if those ropes are perfectly parallel, so forming up, this is basically creating a rectangle. What's being supported can sway back and forth rather easily. So most of the time, when you set up a sling, you actually have those ropes or chains slightly angled inward. When they're angled like that, you try to push this to the side or make it swing, it's not going to do it nearly as easily because the tension on those is holding it in, keeping it from swinging. Because these angles, this basically, if we're extending it, would form a triangle, and it makes a rigid shape, or a more rigid shape. So one of the first things we want to look at in the triangles, we're going to talk about the angles. There are special relationships in angles. The first one we're going to look at here, you don't need to remember the term, but the term is supplementary. Supplementary angles add up to a line like this. So what do these two angles have to add up to if we add them up? 180 degrees. So if I know one of the angles, let's say I know that this one is 72 degrees, I can find this one by subtracting. 180 minus 72 is 108 degrees. The other special angle we run into, what's that little box in the corner mean? It's a 90-degree angle or a right angle. We can have two angles that add up to a right angle or a 90-degree angle. They're called complementary. So if I know that this angle down here is, let's say 38 degrees, this angle up here has to be, 90 minus 38 gives us 52 degrees. Perfect. So that little square box that put in the corner is a square. That's indicating that this is a square corner. It's called a right angle because in construction and a lot of applications, the angle of the wall to the floor should be 90 degrees. That is the correct or right angle. The two walls should meet at 90 degrees. Again, that is the correct or right angle. So the word right does mean literally the correct angle in that application. Well, coming back to the triangle itself then, the triangle is made up of three angles. Those three angles must add up to, does anybody know? 180 degrees. So if I know any two of them, let's say I know that this one is 57 degrees. Let's call this one 74 degrees. We can find this one by either writing an equation and solving it, which I try to avoid throwing too much algebra into it if I can. We can just take 180 degrees and subtract 74 to get 106, and then subtract the 57 to get, 49 degrees? So that angle has to be 49 degrees. So no matter what shape the triangle is, this would be called an obtuse triangle because it has an angle that is bigger than 90 degrees. Let's say that that is 138 degrees. Let me draw that bigger. So let's say this is 138 degrees. And let's say this one down here, let's call it 19 degrees. What would that angle be? Yeah. So we start with 180. Now I could either subtract each of those individually like I did. Minus 138 is 42. Then minus 19 is 23. Or if you're more comfortable, you could add these two angles together first. 138 plus 19 is 157, and subtract that from 180. You're going to get to the same result either way of 23 degrees. Oops, come on. There we go. We can end up in situations where we don't know the interior angle. We might know, or we might be told that this angle out here is 170 degrees, and this one up here is 62 degrees, and be asked to find this one over here. Well, it's just a matter of extra steps. How do I find this angle here?
180 minus 170.
Perfect. Which gives us 63. Then to find this one, 63 plus 62 is 125. 180 minus that is 55 degrees. Not so bad. Now, there is an obscure geometric rule out there. If you get good at this or you find that it's something you're doing a lot, these two angles, come on. Those two angles have to add up to this exterior angle. So rather than doing this subtraction and then going through, you could have just done 117 minus 62. It's a shortcut. Like I said, if you find yourself doing it a lot, you can use that. But I find it's more reliable just to go through the long process and get it if you don't have to do this a lot.
How do you determine which angle to divide the R?
Very good. So the 117 is the exterior angle, where this would be its interior angle. So either of the other two can be subtracted to get these two over here that are not connected to it have to add up to it. So I'll be given one of the two, and I'll be looking for the other one. So yeah, it's the one that is its supplement that doesn't get used. Either of the other two can be used. You bet. So here, let's say that this angle is 112 degrees. This one over here is going to be 127 degrees. Find this one. $15 degrees, good. So we could have just done 127 minus the 112 to get 15. Or we could do 180 minus 127 gives us that this one is 53 degrees. 112 plus 53 is 165. So 180 minus 165 gives us the 15 degrees. So next we want to focus in on right triangles. In a right triangle, because we know that one of the triangles is a right angle or 90 degrees, we can take a shortcut to find a missing angle. If I know that this angle here is 59 degrees, I could do 90 plus 59 is 149, and then subtract that from 180 to get 31 degrees for that. Or, since I know that this angle is always 90 degrees, what's 180 minus 90? 90. I know that these two always have to add up to 90 degrees. So rather than, I could just forget about the right angle completely and just do 90 minus 59 to get that 31 degrees. In a right triangle, the angles that are not right angles are complements. They're complementary. They add up to 90 degrees. Now in this, of course, we don't have time to get deep into trigonometry. We'll mention the trig functions and how to do them quick on your calculator. But in trig, that relationship of those two angles adding up to 90 degrees is a big deal because it allows us to switch from one trig function to another when you're finding pieces of a triangle. For our part here, all we're going to look at is a quick punching in the sine of an angle in your calculator to get an adjustment factor. So in a right triangle, obviously all triangles have three sides. Our sides are broken down into two categories. The legs make the right angle, or the L of the right triangle. The third side then, which is not part of the right angle, it's across from the right angle, it's called the hypotenuse. And so when we label a right triangle, we typically label the legs as sides A and B, and the hypotenuse is side C. Some of you see where I'm going with this. The relationship between those sides, there you go. A squared plus B squared equals C squared. Where A and B have to be the two shorter sides, and C, of course, is that hypotenuse. So A and B are the legs, C is the hypotenuse. Before we get into finding missing sides, one of the first functions this can be used for is determining if a triangle is a right triangle. So if I have a triangle like this and I'm not sure, somebody give me a number between 5 and 20. 17. You had to go for a hard one, didn't you? 17 inches. Let's see, 17 squared. So let's look at this. First of all, if this were a right triangle, which side would have to be the hypotenuse? 145. It is the longest side, so it might be the hypotenuse. Which means that has to be what we're going to use as side C. The other two sides are going to have to be sides A and B. So to check to see if this is a right triangle, we'll do 17 squared plus 144 squared. That's our legs. And we're going to see if it equals 145 squared. Now I'm going to put a question mark here because we don't know if they're equal yet. I don't want to put an equal sign there unless they actually are equal. So 17 squared is 289. 144 squared.
20,700.
So 2020. Oops, got to get an extra zero in there. Okay. 20736. 145 squared. What's 21,025, isn't it? So if we add these up, what do we get? Well, 21,025. That is equal. So that's telling us that this is a right triangle. That is the hypotenuse, so this is a right angle here. Somebody else give me a number between 5 and 20. 5. So go ahead and verify for me, is that a right triangle? It is not. Good. So 14 is the longest side. If this were a right triangle, that would have to be the hypotenuse. So we label that as side C. Again, we're not sure, so I'm going to put a question mark there. 12 squared is 144. 5 squared, 25. 14 squared, 196. 144 plus 25, 169. Those are not equal. So this is not a right triangle. Good. So that's one of the main functions of this formula called the Pythagorean formula or Pythagorean theorem, Pythagorean rule, depending on what book you're looking in, is to verify if that's a right triangle. The other main use for it is to find a missing side. So we're going to start where we know the two legs, and we might know that this is 8 inches and this is 15 inches, and we're asked to find the hypotenuse. So again, it doesn't matter which leg I call A and which one I call B. I'll call the hypotenuse C. So this would be 8 squared plus 15 squared equals that side C squared or X squared. What is 8 squared? 64. 15 squared? 225. If I add those together, I get 289. Now that equals C squared. So how do I find C? Square root. Square root of 289 is 17. So C is 17. I'm going to have you try one. Oops. Find that hypotenuse for me quick. So 7 squared is 49. 24 squared, 576. We add those together. 625 equals C squared. So we square root to get 25 equals C. Now those first couple, I made sure they came out to nice whole numbers for you. In practice, it's not going to be that simple. It can be. But how do we get a useful number out of it? So let's say that this is 11 feet here, and let's go 16 feet here. And that's C. So this will be 11 squared plus 16 squared equals C squared. Well, 11 squared is 121. 16 squared is 256. We add those up to get 377. Now we square root 377, we do not get a happy number. Oh, you get 19.41648878. Now I'm going to leave that in my calculator because it's going to allow us, this is an operation we did a couple of semesters ago. That is feet. But again, we're not going to measure out 19.41 whatever. But we can say that this is 19 whole feet. So I'll write down 19 feet. And in my calculator, I leave that calculation in there and I just subtract the 19 off of it. What's left is the decimal feet. Well, I want to convert that into inches to figure out how much is left. How do I convert 0.41648 into inches? Not divided. Multiply by 12. That is 4.9978 inches. Now, I can keep the 4 inches. I'll take the 4 off of that. Here I'm going to subtract 4. I'm left with the decimal inches. Because on a tape measure, you don't have 0.999 or 998 inches either. Either we got to figure out what unit we're going to, whether it's a 16th, a 32nd, or a 64th. You guys are going to do some precision measurement, so we're going to go to a 64th. So if we're going to a 64th of an inch, we would multiply this decimal by 64, giving us 63.86 64ths. Well, this number has to be rounded. It's between 63 and 64. It is closest to 64, which would be 64 64ths, which would be 1 inch. So, yeah, we go back here, and the 4 inches becomes 5 inches. So if we were measuring this out across here, this would be 19 feet, 5 inches. Does that that process look familiar to people at all? A little bit, yeah.
I missed the part where you got 63.86.
So what we had was we had the 0.99785 decimal inches yet.
Yep.
We had the 4.99. We subtracted off the 4 whole inches. Then we had to look at what fraction do we want to go to. So since we're going to the 64th, we multiplied that decimal by 64. If we're going to the 32nd, we'd multiply by 32. And so yeah, so then we just have to round that to the nearest whole number. So that's finding the hypotenuse. Now if I'm doing this on my own, I'm not writing this out step by step. What I'm going to do is I'm just going to put it in the calculator like this. I start out with the square root, and then inside the square root, I do 121 squared. Oops, not even that. Let me try that again. In the square root, I do 11 squared plus 16 squared. Then I close my parentheses for the square root, and it spits it all out at once. I didn't get the squared in there. There. It spits it all out at once. That's that decimal 19.416487884 feet that we had before. So we're getting short on time here. So let's say if we're going to find a missing leg. So let's say this is 15 inches and 17 inches, and I want to find this side here. Well, I'll call that leg A. This is leg B, and of course this is the hypotenuse. So A squared plus 15 squared has to equal 17 squared. Now, if you're okay with solving an equation, you can just set it up this way and go. What is 15 squared? 225. 17 squared? 289. Now, to solve this equation, I have to get A by itself. So I have to get rid of the 225 by subtracting it. So that would give us that A squared equals 64. And then to get rid of the squared, we square root it. Yeah, square root it. So the square root of 64 is 8. So this is 8. If you don't like solving equations, well, this becomes that missing leg is the square root of the hypotenuse squared minus the other leg squared. So we could have put in just the square root of 17 squared minus 15 squared and close the square root, and we get the 8. So on this triangle, give me another number between 5 and 20. 9. So it says 9 inches and 41 inches. Find that missing side for me quick. Perfect. So yeah, we could just set it up. Hypotenuse squared minus the known leg squared and then square root. So square root of 41 squared minus 9 squared. It comes out to 40. If you don't want an extra formula to memorize, you could have just done a squared plus 9 squared equals 41 squared and solve the equation. Okay. Actually went a little bit over the time I wanted to talk. I want to give you guys some time to start on a worksheet. So I'll give you a worksheet to work on here. We will go over this at the beginning in 2 weeks when we come back, when you see me again. We'll go over this at the beginning of the class, then we'll do a quiz on it, and then we'll have our second part of it dealing with slings and center of mass and all that good stuff.